Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss laws of reflection on the basis of Huygens theory. Let's begin. There are two laws in reflection. The first law of reflection is the angle of incident is equal to the angle of reflection. The angle of incident means the angle between the incident ray and the normal. The angle of reflection means the angle between the reflected ray and the normal. These two are equal in case of reflection. Second law of reflection, the incident ray, reflected ray and normal to that of reflecting surface all lie in a same plane. We have to prove these two laws of reflection by using Huygens theory. Huygens theory basically based upon the concept of wavefront. If we take a point source, the light emitted from that of point source, the locus of all similar points are termed as the wavefront. This is the representation of a spherical wavefront. If the source is a line source, the light emitted from that of light source seems to be as the cylindrical wavefront. Either spherical wavefront or cylindrical wavefront, when we look that segment from a large distance, it is seen to be just like this, which is known as the plane wavefront. To prove reflection on the basis of Huygens theory, let we prefer that plane wavefront. Here x, y are the reflecting surface here is the normal n a. The plane wavefront AB. Plane wavefront taking two rays L M. These rays are perpendicular to that of plane wavefront, that is a plane wavefront. So, the rays are perpendicular to it, and the angle between that ray to that of normal, that is the angle of incident. That angle is same as this angle I. The angle between the incident ray and the normal, that is the incident plane wavefront AB. That angle is angle of incident, that is same as this angle. which is the normal to that of plane. After some time, that point A reaches the point A dash. And point B reaches the point B dash. Which is the normal N dash. L dash M dash. As the velocity of light is c, so the distance between A and A dash is equal to c into t. A dash is equal to c into t. T be the time taken, that ray from A to A dash. From Huygens theory, that primary wavefront is the source for that of secondary disturbance, or we can say secondary wavefront. Same time taken to the point B to B dash, B to B dash, distance will be c, time taken t. Taking A and A dash as radius, taking A dash which is equal to B dash as radius, and A is the center, draw the sphere. Now A dash B dash here, A dash B dash is the tangent to that sphere, which is the wavefront. Taking A as center, we draw the sphere. So A dash B dash is tangent to that of sphere, which is nothing, that is the wavefront, that be the reflected wavefront. A B is the incident wavefront, A dash B dash is the reflected wavefront. So angle normal to this angle is equal to r, that angle also r. Let we choose arbitrarily a point Q. is the point Q. So that point Q after some time it reaches at the point Q dash here through that ray is incident here. Okay, I just read it. We choose arbitrarily a point Q. We choose arbitrarily a point Q on incident wavefront which reaches at Q dash after time t. That Q reaches the point Q dash to that of point K. So the time taken t, therefore t is equal to the distance Qk, time taken for that of distance, and again time taken for that of distance Q dash K. So here the velocity of light is c. So the time will be Qk divided by c, that time required to travel Qk distance, plus K Q dash divided by c, that time required for travel K Q dash distance. The total time taken for that point Q to travel Q dash through that of point K. Now we have to find out what be the value of Qk and K Q dash, taken as equation number 1. From triangle right angled triangle AQK, that is 90 degree. So sin of I is equal to perpendicular divided by hypotenuse. So perpendicular Qk divided by AK. Our requirement is Qk. So Qk is equal to AK sin I. Again from right angle triangle K Q dash B dash, K Q dash B dash, that is 90 degree. So sin of R is equal to K Q dash divided by K B dash, K Q dash divided by K B dash. Our requirement K Q dash or K Q dash is equal to K B dash into sin R. Let we put these two values in equation 1. Therefore equation 1 becomes time taken t is equal to, in place of qk we substitute ak sin I ak by c sin I plus k b dash by c sin r, which is equal to ak by c sin I plus, in place of k b dash I can write a b dash minus ak, a b dash minus ak divided by c sin r. Taking ak sin I write the terms as ak sin I plus a b dash sin r minus a k sin r divided by c, taking the LCM. Here ak as common, we have a b dash sin r plus ak as common sin I minus sin r divided by c. Look at that particular figure. When we prefer an arbitrary point q, that is the different point, so the rays from different points on incident wavefront, the values of ak are different. If we choose q, then ak, if q be that point, then value of ak, if q be again this point, the value of ak will be this much. So various points on incident wavefront, the values of ak will be different. Therefore a dash b dash is the reflected wavefront. Since a dash b dash is the reflected wavefront, so the time taken by all the rays from incident wavefront to reach at reflected wavefront has to be same. We write it for rays, these are time taken. Equation number 2, for rays from different points on incident wavefront, the values of ak are different, since a dash b dash is reflected wavefront, so the time taken by all the rays from incident wavefront to reach reflected wavefront, has to be same. That's why, therefore, the equation 2 should be independent of AK, as AK varies due to the different points on incident wavefront, and the time taken from the points in that of incident wavefront to reach to the reflected wavefront has to be same. Therefore, that equation should be independent of the term AK. Therefore, we write that term sin I, that is AK multiplied with sin I minus sin R is equal to 0. Therefore, as AK does not equal to 0, so the term sin I minus sin R is equal to 0, as AK does not equal to 0, or sin I is equal to sin R. I is the angle of incident, R is the angle of reflection. Therefore, I is equal to R, that is angle of incident is equal to angle of reflection, which is first law of reflection, and that is proved by Huygens theory. Now, the incident wavefront AB, the reflecting wavefront A dash B dash, and the reflecting surface XY all are perpendicular to the plane of the paper. Here is the surface XY, that be the incident wavefront, that be the reflected wavefront, all are perpendicular to that of plane of the paper. Therefore, the incident ray AB, the incident ray, just like either we take LA or MB. This is the incident ray, AB is the incident wavefront, and the normal AN, and the reflected ray A dash, L dash, B dash, M dash, which are perpendicular to AB, XY, and A dash B dash, all lie in that of same plane. This proves the second law of reflection. So, we write the incident wavefront AB, the incident wavefront AB, and reflected wavefront A dash B dash, and reflecting surface XY are perpendicular to the plane of paper. Therefore, incident wavefront, therefore AB, therefore incident rays like LA or MB, and reflected rays for reflected wavefront, that is A dash L dash, B M dash, and normal A N are in same plane, which proves the second law of reflection. Which proves the law of reflection. So, with the help of this visual exercise, you understand, by using Huygens theory, we prove the law of reflection. Taking AB as incident wavefront, A dash B dash as reflected wavefront. These are the incident rays LA and MB. These are the reflected rays A dash L dash and B dash M dash. This is the first law, angle of incident is equal to angle of reflection. Next, second law, the incident ray, reflected ray and normal are in same plane, which proves the second law of reflection. In this way, two laws of reflection are proved by using Huygens theory. So, with this useful and informative notes, let me wind up this session. Thank you.